Okay, this is lecture 3 of our VLSI devices 2025. Once again, due to my business trip to Hong Kong, I have to record this lecture 3. Okay, from lecture 4, I will just do the ordinary offline lecture. Okay, in this lecture 3, we will talk about the transport mechanisms. So when we say transport mechanisms, actually there are two, and one is here, throughput, and the other one is diffusion. So we have to both of these two mechanisms, and let's introduce one by one. Okay, so this is throughput. Throughput is related with net movement of charged particles due to an electric field. So usually we say this one, vector E, is regarded for the symbol as the electric field. And when we have a certain electric field at a certain position, and if we have a certain electron at that position, then the force exerted on the electron is simply given as force is given as minus q times electric field, because electric field is usually defined for normalized force with respect to the positively charged particle. So since our electron is negatively charged, so our electron experience the opposite direction force than the positively charged one. So this is the expression for force exerted on the electrons, and of course for holes we can say this is a positive Q, so don't be confused with this sign difference. So according to Newton's second law, then since we have the force, this is related to the acceleration. So acceleration is given by force divided by effective mass, then this is corresponding to the acceleration vector. So then if we have the initial velocity, so this is the initial one, and after time has elapsed amount of t, then maybe we will have this acceleration multiplied by the time duration. So although initial velocity is small, but if we wait for long time, like several seconds, then we will have extremely high velocity. But everybody understand this is not the case. So if we have a certain electric field, yes, initially our electron is accelerated. For example, if this is the direction for our electric field, then it will be accelerated in the opposite direction. Then initially it is getting more and more velocity. However, the velocity of the carrier does not increase indefinitely. Because why? Because electrons are scattered quite frequently and lose their momentum. So it's like this. So initially it has a certain velocity and it is accelerated. Okay, it is getting faster and faster. However, if there occurs a certain event called as scattering, then its velocity is usually reduced. After that, since this electron is still under a constant electric field, it is further accelerated. Once again, there occurs another scattering event. So if we follow this one, then there will be certain certain behavior of our velocity as a function of time. So if there is no scattering event, then what will happen? So certainly we will have just a straight increase of velocity. However, if there occurs quite a frequent scattering events, then at every event the velocity is lost and lost. So we will have a certain values of velocity even after long time later. So it is known that actually this value of electron velocity after long time has passed under constant electric field is more or less given. I mean that, so if we have a higher electric field, then of course this slope becomes steeper, and if we have lower electric field, so then we will have a relatively slow increase of velocity. This is determined by our electric field. So if we have higher and higher electric field, then eventual velocity will be higher. And if we drive our electron relatively low electric field, then yes, the final velocity will be lower than that of a higher electric field case. So velocity of each carrier can show sharp transition, because every time the scattering events happens, then it will lose considerable amount of velocity, in other words momentum. However, if we consider the gas, electron gas, a set of electrons, then there are many electrons, so their average velocity is not sharply changing, but its shape shows, or its behavior shows some smooth behavior. Although one electron shows quite a steep behavior, and the other one also shows this one. However, its average will show much smoother transition. So as is shown here, the average velocity follows a much smoother trajectory, so it can be written as this form. Okay, so average velocity is still accelerated or increased by electric field. However, if velocity is too high, then there will be certain mechanism to reduce it to zero. So you know this is related with scattering events, and so we can write down an equation for the average velocity. Then if we go to quite a long time, so let's go to t equal to infinity, then let's assume that there exists a certain steady state value. So if we have a certain steady state value, by definition of that steady state, so time derivative goes to zero, then we can say that, okay, so minus QE effective mass minus average velocity Tn. Please note that this average velocity is now steady state velocity, and from this one we can write down velocity. Actually, this is a vector. This velocity can be written as minus Q tau n m n and electric field. Here we have a certain subscript n, and n, these subscripts n's are for electrons, and if we consider, for example, holes, then of course we have to switch it to the subscript p. I think that you know it quite well. And after that, now we have this expression as is shown here, and here we have a certain proportional coefficient of average velocity, steady state average velocity with respect to the electric field, and this coefficient, proportional coefficient, is called as mobility of a certain carrier type. If we consider electron, then this is electron mobility, and of course if we consider holes, then we can consider hole mobility. Okay, mobility has the unit of square centimeter per volt second. Please try to remember this unit system because it is important to know the value. And as you can see here, the value of our electron mobility and hole mobility in terms of square centimeter volt second per volt per second is given as 1000 something or several hundred. But please note that these values are actually extremely high value, which is not achievable in our actual device. So if we have quite pure silicon, high quality silicon without any impurity in it, and yes, in that case we can expect this kind of high value. So actual value should be regarded as just about 100 or even lower value is expected. Okay, and as you can see here also, another one is well, gallium arsenide has quite a high electron mobility. At the same time, it has a relatively low hole mobility. So using this kind of compound semiconductor, we can expect quite high speed devices with electron movement. On the other hand, if we have a look at the germanium, so although germanium mobility, electron mobility is also high, but more pronounced one is here. So compared with this silicon, actually germanium has a particularly high value of hole mobility. And you know that when we have a look at silicon, silicon has much higher electron mobility than holes, so increasing the hole mobility is quite important, or introducing some germanium in it into the silicon devices is a good way to increase especially hole mobility. So we will talk about this technique later if we have sufficient time. Okay, so anyway, let's come back to our discussion. So now average steady state velocity of electron can be expressed as this way. So mobility times electric field, and depending on its polarity, we have a negative sign or just a positive sign, for example for holes. Okay, so then when we have this above relation, so linearly proportional velocity, drift velocity with respect to the electric field, then we can now define current density. Okay, so I will explain what is the current density in the next slide, but now we can have this expression. If you are quite new to this study, then you may feel that, oh, here we have the same sign for this electron and holes. Up to now, we say that electron mobility follows minus mu n e, and also we say that hole velocity follows positive mu p e. Certainly we have a difference due to the polarity difference here and there, but why we don't have any change or any difference in its drift current density? It is because this current density is not for movement of a particle, but it is related with the charge carried by that particle. In the case of our electron, they carry minus q charge, but on the other hand, hole carry positive q. So although negatively charged electrons moves that way and positively charged hole moves that way, if we consider in terms of charge movement, both of them says that relatively positive charge is moving toward that part. So now we have this expression. So before moving into the next topic, so let me just talk about the relationship between terminal current and current density. Current density J can have many different subscripts here. For example, if that is related with electronic motion, then we can say that electron current density. If it is related with hole movement, then we can say yes, this is hole current density. Also, we can define other one. So by combining them all, then we can also define the total current density. So at the starting point, many students are confused with so many different current densities. Why there are so many different ones? It is because this is for electrons, and this is for holes, and this is for displacement current density. So different charge carrying mechanism contribute to different components, but the total current density are just summing them all, and that is a unique quantity well defined here. So J, current density, is current per area. So this is defined everywhere, means that this J is a function of position. On the other hand, let's think about terminal current. For example, already you know what the MOSFET is. So for example, drain current and source current and gate current. When you say drain current, when you say source current, can you define the drain current inside your transistor? Yes, ID. So you never define this terminal current inside your transistor. So actually, if you have, for example, this is your source contact, and if this is drain contact, then drain current is defined on this drain contact, and source current is defined on this source contact. So although terminal current and current density are quite much related one, but they are defined on different places. This is defined on everywhere, and this is only for our terminal contacts. Then what is the relation between these two quantities? It is simply given as this integration. So although J is defined everywhere, but this J is integrated only over a certain terminal. For example, if we consider drain current, then we just integrate the J vector over drain contact, then we will get the drain current. If we do it for the source contact, then we will get the source current. So that's it. And here we have a negative sign because this is the convention. We wanted to have incoming current as a positive one. So I hope that you have already studied this one in your previous courses, and if you don't understand the relation between terminal current and current density, then please review your previous courses. Okay, then now as you can see, there can be different current densities due to the electron, due to holes, and of course, depending on the transport mechanism, the repeat component can contribute, and later also diffusion component can contribute. And anyway, the drift current densities are quite much unified form. So here we have electron density multiplied by electron mobility, and hole density and hole mobility. So if we just sum them all, then we can say that okay, Jn, Jp, these are particle current density, are given as Q times mu n n mu p p and electric field. And you know, this one is corresponding to the conductivity. So this is conductivity sigma, and its inverse is defined as resistivity. Okay, so this one is just inverse of our sigma, and it has the unit like ohm centimeter. Okay, so please check the unit. And yes, I can just skip this one. We may have the chances to discuss this one later. Okay, so up to now we have discussed about the drift mechanism and the occurrence of such kind of steady state average velocity is the scattering. But we have never thought about the physical mechanism to have scattering events. One of the most dominant scattering mechanism inside silicon is phonon scattering. So phonon means that vibration of silicon lattice, and when electrons and phonons are interacting together, then they can just exchange something. Here something means that they can exchange energy, and also they can exchange their crystal momentum. So by exchanging these quantities, so sometimes electrons are deaccelerated, or sometimes electrons are accelerated. And phonons, there are many different phonons, and the common factor is phonons. The strength of a phonon is proportional to the temperature. Yes, because phonons are thermal vibration of lattice, and if we go to low temperature, quite close to the 0 Kelvin, then there will be no phonon scattering at all. Even when we have quite a low temperature, okay, for example, where are we now? We are living around here, so this is roughly 300 Kelvin. Electron mobilities are there, widely spread due to the doping density, different doping density. And we expect that if we go to this low temperature, then actually phonon scattering goes away. But you know that this electron mobility never goes to the infinity. So of course the electron mobility is now increasing and increasing, but it is not that much increasing in this case. For example, in the case of donor density of 10 to the 19 per cubic centimeter, what happens? Although we have reduced the temperature quite much, but the increase of our electron mobility is quite marginal. It means that actually the mobility of electrons shown here is not limited by phonon mechanism, but it is limited by the other one. When you have a look at the relatively low one, 10 to the 14, yes, 10 to the 14 per cubic centimeter, it can be regarded as just almost intrinsic one. In this case, we have a considerable increase. So means that for highly doped sample, actually mobility is limited by its impurity scattering. And if we go to lowly doped sample, then actually this mobility is limited by phonon mobility. And if we reduce the temperature, phonon mobilities increase quite much. So that is shown in these graphs. Okay. So from this consideration, it is true that if we have sufficiently high doping density, actually the electron and holes mobility is limited by impurity scattering. So yes, so this is the table or figure which shows the mobility as a function of impurity concentration. So you know that 14, 15, yes, these numbers are almost intrinsic, nothing. Even 16, you know that here the mobility shows quite much unchanged value. Of course, you can see that a slight difference, but compared with this huge drop here, so almost there is no difference at all. But if our impurity density is higher than, for example, 10 to the 16, now it starts to roll up and roll up, and later actually in this part the mobility is limited by this impurity concentration. So which one is dominant? So certainly we have two different competing mechanisms. One is phonon and one is impurity. Then if we have a very high doping density, then of course impurity will be the dominant factor. And if we have a relatively low impurity density, then phonon will be a dominant factor. Then what is the boundary between this importance of phonon and impurity? In the case of 300 Kelvin, now we can say that more or less 10 to the 16 per cubic centimeter is the boundary. But this is at 300 Kelvin. If we reduce the temperature a little bit, then phonon scattering is become weaker, and the onset of impurity limited mobility comes earlier. Okay, then how can we make the overall mobility out of individual contributions? So it follows Matheson's rule, so inverse of each contribution. So here mu I is impurity limited mobility, and here mu L, this is related with phonon limited mobility. I guess that maybe this L is corresponding to the lattice, and please remember that phonon is the summer motion of our lattice. Okay, so as I shown you before in the previous slide, so when there are multiple contributions to the mobility, then actually we can say that the sum of their inverse, and eventually this sum is once again inverted, and that will give us our total mobility. So up to now we have thought about the average steady state velocity, but when this velocity is so high, then actually this one, contribute also kinetic energy. So this kinetic energy can increase the average energy of our electrons. So if we apply quite a high electric field, then our electrons or holes average energy can deviate from its equilibrium value. That is quite normal to have this kind of behavior. And another important behavior is velocity saturation. Up to now, we have thought about this one. The average electron velocity is just given as this form. For example, let's say that 1000 meter per volt per second. And if we apply, for example, 1 kilovolt per second as the electric field, then what will happen to our velocity? So here we have 10 to the 3, and this 1K is also corresponding to 10 to the 3, so we will have 10 to the 6 centimeter per second. That will be the velocity of our electrons. Yes, so if we increase the factor to kilovolt per second, then what will happen? Following this expression, we will guess that, okay, now we have 2 times 10 to the 6 centimeter per second will be the steady state drift velocity. Yes, it's true, but if we go to even higher and higher electric field, then what will happen? For example, if we apply 1 megavolt per centimeter, then do we have really 10 to the 9 centimeter per second as an electron velocity? Actually not. It's not. Please regard this expression, the linear proportionality between the drift velocity and the electric field, as an extreme form which is valid for small electric field. For small electric field or low electric field, it's true. However, if we go to a higher and higher electric field, actually the amount of scattering experienced by our high energy electron becomes rapidly increasing, so velocity cannot linearly increase any further. So simply speaking, if we draw the electric field, the magnitude of electric field, and let's say the also its magnitude, then if we have a zero electric field, then zero velocity, and there will be certain slope, and this slope is corresponding to the mobility. However, when we have quite a high electric field, it never increases indefinitely, so eventually it is saturated, and there occurs certain maximum velocity we can have with these electrons or holes. So this is the graph. So if we just draw the velocity as a function of electric field, so you know this is the electric field, and this is velocity, and it's absolute value, and you can see that this is log graph. So both of x-axis and y-axis are written in the logarithmic scale. So this one decade by one decade, that is corresponding to the linearity. And as you can see here, electrons and holes shows quite a good linearity up to, for example, 10 to the 3 volt per centimeter. So 1 kilovolt per centimeter. However, if we go to 10 kilovolt per centimeter, then how does it look like? If we have just linear proportionality, then maybe we would have this value, but already we have quite much reduced value of carrier velocity. And eventually when we go to quite a high electric field, what is high? It's around 100 kilovolt per centimeter. In this case, now we have more or less almost constant value, and we say that the velocity is saturated. Regardless the type of our charge carrier, electrons and holes, both of them are around 10 to the 7 centimeter per second. Okay, so don't be confused with our previous expression like velocity is proportional to the electric field. This relation is still valid, but where is the valid reason for this relation? Yes, this is valid in this part. If we have high mobility material, then what will happen? For example, if we have 10 times higher electron mobility, then what will happen? In this graph, our electron mobility graph will just move that way. And as much as this linearity holds, then we will have this straight line. So higher mobility just shows increase of this linear graph. It is nothing related with this high field saturation. At high field, so most material shows similar behavior. Their velocity is saturated to some values depending on the material. This velocity saturation is very important. So it is expressed in this or that form. We must understand this so-called Cauchy-Thomas relation, whatever. So here we have V sub S and V sub S. What is this? This is saturation velocity. And this is about 10 to the 7 centimeter per second, regardless the type of electron and hole. And now we have a certain electric field dependence here. And what is actually the electric field? The electric field, you can find it here. So if you have a quite a low electric field, so let's just think about this one. So if we have quite a low electric field, small electric field, then what will happen? Actually, this number becomes quite large because this is located in the lower part. So compared with this number 1, actually for small small value of E, then it will just become E on over E. Are you with me? Because it's gone, and this power 2 and power 0.5 combined together and yield just the power of 1. So now we will have Vs divided by E on and electric field. What is this? This is corresponding to our electron mobility. Same situation follows for whole expression. So we will have Vs, E, O, P, and E, and BS EOP multiplied by E, and this is corresponding to the whole mobility. So in the case of low field limit, when the value of E goes to almost zero, then in both cases we are reduced to velocity equal to mobility times the electric field. Yes, it's good. And now let's think about the opposite direction. Now we have quite a high electric field. Then what will happen? Its behavior is easily understood. If we have almost infinity electric field and infinity one, then actually this term will rapidly approach to 0 and 0, and this entire term will become saturation velocity. So from this Cauchy-Thomas relation, what we can say is following this one, then E and V, and there is linearity, and this one saturation velocity, and this is mobility, and both of them provide smooth transition between these two extreme levels. But why do we have different models? Here we have 2, 0.5, and 1 and 1. If we have 1 and 1, then it shows relatively smooth transition. And if we have this power of 2, then the transition becomes more abrupt. So since electron and holes inside the silicon material have different band structure and scattering mechanisms, so that's the reason why they have different intermediate behavior in this electric field range. So they are modeled with different values, but it really depends on the model. Up to now, we have thought about the phonon scattering and also impurity scattering mechanisms, and also later we have thought about velocity saturation. Velocity saturation is quite important, and now we can consider other scattering mechanisms. All of this phonon scattering and impurity scattering can be found even in other devices, not surface channel devices. For example, BJT or PN junction. For those devices, still we have a phonon scattering and impurity scattering. But if we consider MOS device, which use the surface channel as the main conducting channel, then actually we have additional scattering mechanisms. Unfortunately, actually these other scattering mechanisms are dominant in the case of our MOSFET. So combined with these phonon and impurity scatterings, we have additional scattering mechanisms specifically important for the MOSFET, and we must consider also those ones. So I hope that maybe in later in this semester we have some time to more deeply discuss about these scattering mechanisms. Okay, up to now we have thought about the drift mechanism, and now we switch it to the diffusion mechanism. So in the case of diffusion, in contrast to the drift, the driving force is not the electric field. It means that even when there is no electric field, but still diffusion can occur. So it is related with this difference, spatial inhomogeneity of our electron density or hole density, and you can see that the movement of our electron is given by this form. So here we have a negative sign and gradient of n. So gradient of n is heading the rapid increase of or steepest increase of electron density. So this negative sign means that electrons are moved from the highly populated region to the or lowly populated region. So electrons are moved from this part to that part. And here we have also proportional coefficient. And this proportional coefficient is called as diffusion coefficient, and it is written in the unit of square centimeter per second. When you remember the unit of our mobility, and it has the form square centimeter per volt per second. Okay, there is a difference in the per volt unit. And in the case of this is the flux, and it can be converted into the current density by multiplying the charge carried by this charge carrier. In the case of our electrons, they carry minus q. So by multiplying minus q to this flux term, then now we have positive q dn gradient of n. On the other hand, in the case of holes, now our whole flux is also having the same form, but when we multiply positive q to this one, actually we have a different sign. So now I will just combine these two mechanisms. One is electron and one is hole. In the case of electron current density, we can make the contribution due to the drift mechanism, and this is corresponding to the diffusion mechanism. Also, in the case of holes, we can identify hole drift component and hole diffusion component. In addition to these two particle current, we can introduce a displacement current density, which is given as the time derivative of displacement vector. And if you don't understand this one, then please study the electromagnetics. Okay. And at equilibrium, we can also assume the Einstein relation, the relation between our mobility and diffusion coefficient. So you know that this one has the square centimeter per volt per second, and this one has square centimeter and per second. So I told you that the difference is this volt unit, and in order to match them, so we have certain voltage unit quantity, and this is nothing but summer voltage. So summer voltage is the summer energy divided by Q, and of course at 300 Kelvin its value is 25.85 millivolt. So by multiplying this volt unit to the mobility, then actually this per volt unit is gone and they are matched. This Einstein relation is strictly valid only at equilibrium. yes, it is not generally valid, but in our treatment, in this case, we will use this expression even for our non-equilibrium case. So how can we justify this use of Einstein relation to non-equilibrium cases? Actually, it is really difficult to justify ourselves. We will just use it and hoping that the amount of error introduced by this assumption is not that high. Okay, so then if we introduce this Einstein relation, then we can find a further simplification. So now let's consider this one. Electron current was given as a Q mu n n E plus Q d n gradient of n. By applying the electrostatic approximation for this electric field, so now you can say that minus Q mu n n gradient of phi. This is drift term, and now we know that this is corresponding to the mobility multiplied by Summer velocity. So what we can say is mu n also Summer velocity. This is d, and now we have gradient of n. So by combining them all, then we can identify the common factor Q mu n n. Yes, this is corresponding to the contribution to the electric conductance, and this conductance is taken. After that, now we have this form minus kBT Q. Well, although we have took this electron density, but actually in this diffusion part we don't have electron density, so therefore we have to introduce another 1 over n here. Yes, now we have this form, as you can see here, and we can follow the same technique for whole current density. So simply speaking, let me just write down in this way. This means that electron current density can be written as minus sigma n, the conductivity originated from the electrons, and something. So usually if we have something here, what will be this something? The something will be some quantity corresponding to the electric field. However, please note that in this case it's not. This one is really corresponding to the electric field, and this is the drift component. However, we have the modification originated from diffusion component. Also here we have modification due to the diffusion component. Both of drift component and diffusion component can be combined. And now let's go to the next page to be even further simplification. So previously, in the case of equilibrium case, we were able to express the electron density in this form. So it was studied in our lecture 2. And here we have intrinsic formulable, and this is formulable. And in this case, we have introduced something like this. EI, this is intrinsic formulable, and in order to represent this intrinsic formulable, we have introduced minus Q times phi, and this phi is called as what? It is called as electrostatic potential. So also in order to express this Fermi level, then now let's write down in this phi f, and let's call it as Fermi potential. Yes, if we just introduce minus q and minus q, then how can it write down? And I, intrinsic carrier density, is there, and exponential, and now we have minus q all over there. So now we will have kbt over q, and negative sign is gone, and now we have a phi minus phi f. So we can write down here following the same procedure. So we can write down the whole density in this way, and I, and this one will generate minus q times phi, and this one will generate minus q times phi f. So we will have exponential minus kbt over q, and here we have phi minus phi f. They are Tauer's equation 2.49 and 50. Yes, so what is the difference between the previous one and a new one? There is no difference. We just introduce a little bit different expressions. Previously they were expressed certain energy variables, and now we have introduced potential variables. That's it. Up to now everything is just perfectly the same, but here in the next slide we introduce a bold generalization. So here we have phi sub f and phi sub f, which is corresponding to the Fermi level. At equilibrium we can easily define the Fermi level without any difficulty. However, in the case of a non-equilibrium case, actually there is no quantities corresponding to E sub f, so we don't have it. So actually we cannot apply this expression. What expression? N equal to Ni exponential phi minus phi f divided by summer voltage. This expression looks quite attractive, but it is valid only at equilibrium case. But this one is so good, so we wanted to use this one. Okay, if we cannot define this one, then let's introduce a generalized quantity. Then if we define this generalized quantity, then we can still make this equality holds. It means that actually when we have electron density and electrostatic potential, we will just adjust this black box or blue box in order to make this equality. So this black box quantity is called as electron quasi-Fermi potential. So what is the difference between phi f? It was called Fermi potential, and it didn't have any specification because at equilibrium we can uniquely define this Fermi potential. However, in the case of this newly defined quantity, we have two additional specification like quasi electron. Means that quasi means that there is no such quantity in reality, so we just introduce a certain fake quantity corresponding to, in order to make the relation. So this is not the real Fermi potential, so quasi Fermi potential. And even when we try to fit our electron density and hole density by using these two expressions, there is no guarantee that we can find the same quasi Fermi potential. So therefore, we need to introduce separately electron quasi Fermi potential and hole quasi Fermi potential. So that is something. So simply speaking, actually these quasi Fermi potential and these electron quasi Fermi potential and hole quasi potentials are just matching functions to satisfy this expression. Then how can we know this phi and phi p? Actually, this one do not introduce any further information about our problem, just specifier. However, that is quite convenient, so we will love it. So these phi n, phi p are called quasi-Fermi potentials. So for equation 2.61, we must introduce electron 1, and for another one for holes, we need to introduce the hole quasi-Fermi potential. Well, in this slide, I just try to introduce electron and hole quasi-Fermi potentials, and maybe you may think that, oh, why we have to define those quantities. But please, let's have a look at its gradient. That will give us quite interesting behavior. So now from this equation 2.61, let's try to make a gradient of this electron density. Then gradient of electron density will follow this form. Yes, now this is constant, so it is not affected by this gradient operator, and exponential something, but still exponential is still exponential even after we take this gradient. Then later we must consider gradient of its input argument phi n kbt over q. So simply speaking, what is this? This is nothing but just electron density. So if we go to this step, 1 over n, gradient of n is corresponding to 1 over summer voltage and gradient of phi minus phi n. Oh well, maybe you feel a little bit strangey, so let me just do a little bit further. So when you have a look at this one, now you can make it this way. kBT over Q, summer voltage is moved to the left hand side term, and 1 over n gradient n equal to what? V minus gradient phi n. From this expression, now I can summarize in that way. Gradient of quasi-Fermi potential is equal to gradient of electrostatic potential minus summer voltage 1 over n and gradient of electron density. So what? this expression is a direct consequence of this definition. Starting from equation 2.61, there is no other trick. Just direct manipulation gives us this form. But point is, now this one is corresponding to this part. How does it look like? You may now understand this entire term can be written as just a gradient of electron quasi-Fermi potential. So now let's finally come back to this term. Now electron current density can be written as minus electron conductivity times something. Previously, when we considered only drift component, that was the gradient of electrostatic potential. But even though when we consider this diffusion term, but still it can be written as gradient of our electron quasi-Fermi potential. So the role of electrostatic potential now can be done by this electron quasi-Fermi potential even when diffusion component is included in our transport behavior. So simply speaking, this one, gradient of electron quasi-Fermi potential, is the driving force for electron movement. Also quite similarly, so we can define the whole current density, and now we can define similar quantity. Now gradient of whole quasi-Fermi potential can be regarded as the driving force of our whole movement. So that is already shown here. Yes, I just spent some time to derive this expression. So finally, we can write down this way. Electron current density can be written as electron continuity times gradient of quasi-Fermi potential. And in the case of whole conductivity times gradient of quasi-Fermi potential. These are quite important relation we will use later on. So now gradient of quasi-Fermi potentials can be regarded as driving forces. That is important one we will have. And since this quasi-Fermi potential is so important, so we wanted to know the quasi-Fermi potential. But actually quasi-Fermi potential, as I told you before, it is not a usual solution variable our consideration. So once after we have the electrostatic potential and electron density, then from these two numbers we can recalculate this electron quasi-Fermi potential. But conceptually it is quite useful. But anyway, we wanted to know the boundary condition for these two quasi-Fermi potential. Fortunately, we have these two rules. So at terminals, here terminals means that source, drain, gate or something. So say that this is a source and this is a drain, and you apply just 0 volt to your source and 0.7 volt for your drain terminal. Then how about the boundary values of electron quasi-Fermi potential and whole quasi-Fermi potential? So fortunately for this case, yes, we can say that phi n equal to phi p equal to 0 volt. And in this case, phi n, phi p, they are equal to drain voltage 0.7 volt. So simply speaking, at terminals, both of electron quadriform potential and hole quadriform potential are matched to the applied terminal voltage. And how about the other part? They are contact, and for example, for this part there is no contact and no current flux is allowed. So please note that the current is proportional to sigma n and gradient of phi n. So if this number is not 0, then there will be current conduction through these boundaries. So simply speaking, if we don't want to have any kind of a current conduction at the boundary, then actually the normal component, surface normal component of our gradient phi n and gradient phi p should vanish. So that is the boundary condition for our phi n and phi q. Okay, let me just wrap up today's lecture 3, and we have introduced drift and diffusion, and we have discussed about some important scattering mechanisms and velocity saturation. And at the later part, we have introduced electron quadriform potential and hole quadriform potential, and by using these quadriform potentials, our drift and diffusion components can be merged into quite unified form, and that is quite convenient for our later use. Okay, that was the main contents of today's lecture, and now this is the end of our pre-recorded lectures, and from lecture 4 we will come back to the ordinary offline lectures. And thank you and see you soon. Bye.